Hey everyone, and welcome to The Explainer. I am absolutely thrilled to take you through a frankly mind-blowing shift that is happening right now in the world of technology. For decades, quantum computing felt like it just belonged in a sci-fi movie, right? Or maybe buried deep in some top-secret university lab. Well, scratch that. That era is officially over. Today, quantum is rapidly becoming a booming industrial reality. And right at the center of this incredible transformation is Scotland, orchestrating what can really only be described as a massive 10 billion pound quantum leap.
Okay, let's dive into this. $1.3 trillion. Let that number sink in for a second. That is the forecasted total global market value for quantum technology by the year 2035. The economic stakes here are literally astronomical, and nations all around the globe are right now in this high-stakes, flat-out race to capture their share of a completely transformative industry.
So here is our roadmap for today. We're going to be covering 1. The second quantum revolution, 2. Scotland's secret photonics edge, 3. Securing the supply chain, 4. Solving real-world problems, and finally, 5. The 2035 quantum vision. Let's jump right in.
Section 1. The second quantum revolution.
This whole expansion strategy is firmly anchored by the UK National Quantum Strategy. It's a massive 10-year, £2.5 billion commitment that was launched in 2023. Now, to capture 15% of the global market with that kind of backing, a major shift in mindset is required. The goal? Moving from being a low-risk research and development hub into a high-velocity commercial environment. National policy is essentially providing the crucial capital and the regulatory air cover necessary for Scotland's existing tech ecosystem to aggressively scale up. And by the way, that ecosystem already integrates light technology, quantum, and advanced sensing to generate about £4.2 billion annually. So the runway is completely cleared for rapid commercialization.
Moving on to Section 2, Scotland's secret photonics edge.
Now, you might be asking yourself, why Scotland? Well, it really comes down to a centuries-old engineering heritage combined with a very modern, built-in pick-and-shovel advantage. Think about it. In any gold rush, you absolutely want to be the one selling the shovels. And in the quantum revolution, those shovels are photonics. It's the science of light, providing the essential hardware like hyper-precise lasers and detectors required to actually manipulate these delicate quantum states. Now, what's really interesting about this slide is Scotland's massive export advantage here. Their photonics sector is a robust £1.5 billion industry, and a staggering 98% of its output is exported internationally, heavily to places like the US, Germany, and Japan. This is huge. It means as the global demand for quantum hardware surges, Scotland doesn't have to build a trade network from scratch. They already have a heavily utilized, ready-made international trade pathway.
And the global scientific and business communities are definitely recognizing this infrastructure. In a 2025 report ranking the world's deep tech epicenters, Greater Glasgow ranked 5th overall worldwide. It is holding its own against traditional heavyweights like Cambridge and the San Francisco Bay Area. It particularly stands out with a fantastic global ranking of 4th in collaboration intensity. They have proven they excel at forming international partnerships and, crucially, translating complex academic research into actual viable spin-out companies.
All right, Section 3. Securing the supply chain.
As this technology approaches early deployment, the global landscape is becoming, well, much more complex. International supply chains for these highly advanced components are incredibly vulnerable. And we're seeing a significant tightening of export controls globally on emerging technologies. Because of these vulnerabilities, there is a massive push right now for a sovereign supply chain. That means having the domestic capability to design and manufacture critical quantum components, reducing dependence on vulnerable international foundries. A perfect example of this is a University of Glasgow spin-out called QuantCore Technologies. They are currently the only company in the entire UK manufacturing niobium-based superconducting circuits. That's essentially the ultra-cold, highly specialized wiring required to make quantum chips work. By building and funding this capability locally, Scotland ensures it can secure the physical hardware layer of the quantum revolution without having to rely on outside actors.
However, true technological progress cannot happen in total isolation. In April 2026, the UK hosted the Quantum Development Group in London. This vital summit brought together 13 like-minded nations, including the US, Canada, Japan, and Australia, to coordinate on exactly these issues. Their goals focused heavily on supply chain resilience, research and investment security, and creating strategic international standards. It's really about building a safe, sustainable, and open global market, but doing so among trusted collaborative partners.
Which brings us to Section 4, Solving Real-World Problems.
Let's pivot from high-level policy and hardware into the tangible human impact. Because all of this infrastructure and funding is ultimately about solving incredibly complex challenges through initiatives like the Spark program. So I want to ask you directly, but what exactly will these quantum computers do? It's so easy to get lost in the physics of qubits and superposition, right? But how does this abstract technology actually apply to your everyday life, your health, or your environment? Let's look at 3 powerful, real-world examples that have already been tested.
First up, let's look at your wallet. Financial fraud is a massive, incredibly sophisticated issue today. Spotting a single fraudulent credit card transaction hidden in a mountain of legitimate data is incredibly difficult for standard classical computers. It's like finding a needle in a digital haystack. Well, a proof of concept by Unisys explored using quantum-restricted Boltzmann machines, which is essentially a highly advanced quantum algorithm designed to find hidden patterns for this exact task. And despite the challenging data, the quantum model demonstrated remarkable performance, achieving no false negatives and very few false positives. It is separating complex data patterns far more effectively than we've ever been able to do before.
And this brilliantly illustrates the life-saving potential of the technology when we look at healthcare. Take liquid biopsies, which are a minimally invasive way to detect cancer early just from bodily fluids. Applied quantum computing led a project using quantum machine learning classifiers to analyze this incredibly complex biopsy data. The quantum classifier successfully distinguished between different cancer cell types with an incredibly high predictive performance, actually outperforming classical deep neural network methods in certain cases. This translates directly to faster, more accurate early cancer diagnosis and much better patient outcomes. Finally, let's look at the environment and climate action. Scotland has a massive renewable energy pipeline of over 84 gigawatts in capacity. Just to put that into perspective, that is a truly monumental scale of clean energy production. But figuring out exactly where and how to place hundreds of offshore wind turbines to maximize their collective energy production, that is a mind-boggling spatial optimization problem. Working with Fraser-Nash Consultancy, researchers successfully used photonic quantum hardware to model and optimize these turbine layouts. It's literally a game changer for spatial planning and for hitting net zero targets as efficiently as possible.
Section 5. The 2035 Quantum Vision.
Having seen the incredible potential of these near-term applications, let's zoom back out for a second to the long-term roadmap. Let's move to and see how this builds on the Scottish Technology Council's framework to hit that staggering £10 billion revenue target by 2035. They've laid out a really comprehensive 10x growth strategy to basically remove all the friction from the innovation journey. It involves attracting 10x global capital into a £100 billion National Economic Investment Fund. It requires a 10x increase in spinouts by heavily supporting founders so they don't pack up and leave for the US. It leverages 10x purchasing through public sector demand. And finally, 10x visibility, cementing their unique leadership in semiconductors and photonics on the international stage.
The transformation they are engineering here is massive. They're moving from their current state as the 5th-ranked global cluster to a future goal of becoming Europe's leading AI-ready nation. And notice that connection. The roadmap proposes 5 gigawatts of sovereign inference data center capacity. What that means is locally controlled servers dedicated entirely to running massive AI models. Because you see, quantum computing and artificial intelligence are intrinsically linked. Quantum machine learning protocols are expected to completely revolutionize AI applications. By securing clean energy and sovereign infrastructure right now, Scotland aims to meet the colossal computational demands of the 2030s head-on.
So the crucial point is this. We are no longer just looking at a fascinating scientific experiment in a lab. We are actively watching the architecture of the next global economy being built in real time, leveraging legacy strengths to forge entirely new ones. Which leaves us with a massive question as we rapidly approach the quantum century. Will the integration of quantum computing be the ultimate driver of national prosperity, security, and global influence in the 2030s? Looking at this strategy, it certainly seems that way. Thank you so much for joining me on this explainer, and definitely keep your eyes on this space.